Okay, team. Let's dive straight into today's architectural explainer. We're ripping apart the legacy OS paradigms and getting right down to the cold, bare metal of our display pipeline. As fellow engineers grinding on the Sex microkernel, you already know we're not just hacking together another Unix clone. No, we're building a mathematically provable, single address space OS, a strict SAS OS. And to actually pull that off, we have to completely rip up the playbook on how pixels physically reach the screen.
Now think about the visual liveness guarantee we codified back in phases 31 and 32. This isn't just some abstract guideline, it's our physical reality. The mandate is crystal clear. If we don't actively alter the frame buffer on every single scheduler tick, our kernel has officially failed. A no output state is literally illegal. Every time our display server, SexDisplay, loops, it absolutely must produce either a valid UI frame or a distinct idle frame, like a dark purple base with a moving cyan stripe. And if it hits a corrupted or unknown opcode, it paints a massive bright red error strip. We don't guess. The hardware enforces this contract.
And this is exactly why we've had to completely abandon Linux and POSIX assumptions. If you look at standard desktop Linux, it's just drowning in libc overhead, threads, and these wildly unpredictable Wayland compositor loops. But our reality in SexOS, it's radically different. We're operating strictly in a no_standard, zero-thread environment with perfectly bounded weights. Our microkernel enforces absolute ironclad isolation using Intel memory protection keys. You won't find a single cross-domain pointer here unless it is explicitly mapped. We rely 100% on PDX for zero-copy IPC. And the golden rule? SexDisplay is the absolute sole writer to the frame buffer. End of story.
Let's actually trace the physical route a pixel takes through our proven phase 60 pipeline. It starts with Silk Shell. But here's the kicker. Silk Shell doesn't render pixels at all. It simply emits pure UI intents, what we call our UIR. Those intents fire across the PDX capability edge, specifically routing through slot_display, which is locked down tight under MPK hardware constraints. From there, it hits SexDisplay, gets mathematically compiled into a DRM atomic commit, and is shoved directly to the EDP hardware scanout. It's a continuous, totally deterministic stream from intent to photons.
But the real paradigm shift we need to internalize here is that we are no longer building a Wayland compositor. I'll say that again because it's absolutely crucial. SexDisplay is not a compositor. It is a display state reduction engine, or DSRE. We aren't just blindly queuing up frames and crossing our fingers that we hit the monitor's refresh window. Instead, the DSRE acts as a mathematical state reducer. It wakes up exclusively on the vBlank interrupt, samples the global scene graph perfectly, and continuously races the hardware scanout. We are perfectly synced to the physical beam of that monitor.
To pull off that flawless vBlank sampling, especially when we're pushing 360 Hz on hardware like the Alienware X17R1, we had to enforce some brutal back pressure. That's where the SFDP comes in, the single-frame depth deterministic present pipeline. We wanted to guarantee ultra-smooth motion without tearing and without any of that weird queue buildup you see in legacy systems. So, we did the unthinkable and just completely eliminated speculative rendering latency altogether.
The absolute critical invariant here boils down to one simple number. Exactly one. At any given nanosecond, there is at most one unsignaled GPU frame in flight per CRTC. If a rendering capsule runs even a fraction of a millisecond late, we just drop the submission entirely. We literally never accumulate latency debt. In our system, the hardware is the only clock that matters.
To manage a pipeline this tight, we enforce a ruthless opcode contract on slot 5. Keep in mind, SexDisplay owns the frame buffer. When Silk Shell fires opcode 0xD, we allocate a buffer. But what if the queue is empty? We get 0x00, the PDX_empty signal. And that explicitly tells us to render the idle frame. We never, ever just spin our wheels blindly. And silently dropping an opcode? That entire concept has been liquidated from our architecture. If an opcode is unknown, the screen goes red. No exceptions.
Of course, getting to this point was a total nightmare. Remember the ghost black screen bug? We narrowly survived that one. It was a catastrophic ABI hazard sitting right on syscall 28. Because our microkernel is built to be incredibly asynchronous, a hardware interrupt could actually fire in the exact microsecond between a ring buffer dequeue and the sysret instruction. When that interrupt fired, it clobbered our RAX register straight back to 0, and since we were using 0 as a no-message sentinel, SexDisplay would just silently stop rendering. It thought its queue was empty, even when it had a massive stack of draw commands waiting. Just a total silent desync.
So how did we fix it? We patched that hazard permanently in phase 25. We completely threw out the raw rack's null sentinel.
Instead, we locked down a typed register contract where type ID 0x00 is now strictly, exclusively reserved for empty messages. Our output contract is now registers only. No memory-backed syscall return structs anywhere. This fundamentally makes our IPC contract mathematically deterministic. It's completely immune to interrupt clobbering. The ghost bug is officially dead.
We also finally crushed that headless compositor issue, where the screen would just hang on black during boot. The root cause was wild. SexDisplay was perfectly alive, but Silk Shell literally had no authorized hardware route to talk to it. We solved this right in the boot DAG. Now, we explicitly wire the slot_display capability edge to Silk Shell directly inside init.rs using pd.grant capability. Before a single line of userland code even executes, the hardware MPK locks are already pre-configured to allow that handoff.
All of this architectural groundwork ultimately enabled our shift to the FDPC, the fence-driven plane graph compositor. We've totally liquidated the legacy idea of mutating an active persistent frame buffer. Instead, we build an immutable artifact lattice. We map gem-dumb buffers, we manage atomic lease-based ownership, and we execute KMS atomic page flips that are strictly synchronized with fences. You acquire, you render, you fence, you release. The result? Zero tearing. Ever. And because we're relying on atomic KMS commits and state reduction instead of a persistent rendering loop, we are able to build out the silicon resurrection system. Say our primary renderer, like the massive DGPU, just completely hangs or crashes. The SRS kicks in as a last good frame latch. It mathematically guarantees visual liveness. The system will literally never pass a null pointer to the scanout beam. We can completely restart the back-end rendering subsystem while the display itself stays beautifully alive and stable.
So that covers our foundation. We've successfully built this proven metal-bound pipeline with the DSRE, the SFDP invariant, our hardened Syscall 28 ABI, and solid Intel iGPU scanout. But now we need to talk about what happens next. It's time to map out the immediate frontier for the display team.
Our next targets are dense and we're moving fast. First up, executing the NVIDIA Prime Optimus handoff. We're leveraging DEMA buffs so the NVIDIA DGPU can churn through complex graph rendering, and then we'll just pass that file descriptor straight over to the Intel iGPU for pure scanout. Second, we are completely eliminating Wayland. We aren't building a shim to emulate it, we're routing legacy apps through a lattice shim directly into our native scene graph. Third, we need to finalize the universal UIR compilation. And finally, we're smashing past Intel's 16-key hardware limit by implementing Revo key multicast, allowing us to dynamically rotate MPK domains across massive high core count servers. So team, I'm leaving you with this. The hardware is sitting there, actively waiting for our exact IOTCL sequences. We have the architecture locked in. We have zero-cost MPK isolation working flawlessly. The question is, are we truly prepared to execute a complete Wayland elimination and mathematically guarantee 360 Hz visual liveness across the entire silicone lattice? Let's get back into the codebase and make it happen.